So welcome to my project presentation on title Price with a Smile. This is a production style local volatility surface and backtest. So overview of the project. In this project implements a backtest of a local volatility, a Dupire type pricing and hedging framework compared against a Black-Scholes sticky implied volatility baseline. And I use real market options data obtained from Polygon over multiple consecutive trading days over the span of a month. The goal is to assess to assess the out of sample delta hedged P&L stability and the pricing RMSE, the pricing error across these models, and to check whether the local volatility surface in fact provides a more consistent hedging performance than the simpler Black-Scholes sticky volatility model. The motivation of this project was to build a realistic end-to-end quant research project on local volatility that sort of mirrors the kind of work a junior quant researcher would do on a daily basis, including cleaning market data, building arbitrage-free surfaces, calibrating models, pricing, hedging, and so on and so forth. So let's get into it. We start with obtaining the quotes data for each day, the NBBO quotes data at the end of each day, and we choose to focus on the SPX option quotes. We obtain both the calls and puts, and you can see a snippet over here of what my quotes data looks like. I obtain the expiry, the maturity, the expiry, and the strike price, the price, and the bid and ask, especially since it's a real market data, and I compute the mid using the bid and the ask. And I also obtain the index data, which is the SPX index. The next thing we do is match the call and put pair and calculate the forward price using the call put parity. You can see a snippet of my forwards table over here, and for now I set keep the interest rate to be 0. And I also use my from my forward and the spot I also obtain the dividend yield curve. Another snippet of that is also provided over here. The next thing I do is I calculate the implied volatility using the Black-Scholes formula, as we have done in our course. I merge the quotes with the forwards and the curve and the dividend curve data, and match the Black-Scholes formula to the mid prices. From there, I get the IV table, which is the implied volatility table. And my next goal is to fit a arbitrage-free price surface. And in order to do that, I choose to work with the undiscounted forward call prices, as shown over here. And this so that both calls and puts map to the same object, which is the forward measure call price. You can see the implied volatility smiles, or rather in this case, the smirks, because this is SPX data. There is for a single smile at t equals to 0.0192. This is what it looks like. But on the right hand side, you can see a different graph, a different plot, where you can see that with increasing the maturity, the implied volatility surface moves up. Like I said, we'll be fitting an arbitrage-free price surface. In order to do that, what we do, we build a tensor grid of maturities and the per maturity strike prices. And we then we solve a convex optimization problem to fit this surface to the market data. And we split it in such a way that it satisfies certain no arbitrage constraints. So the two parameters that you can see over here, lambda kk and lambda tt, are the parameters that impose those constraints. And in particular, the constraints that we choose to work with are the bounds, that the fact that the call option prices are within a certain bounds and they're monotone in strike. That means the price decreases with an increase in the strike. And they're convex in strike. In particular, the second derivative of the call option price with respect to the strike price should be positive. And we also impose calendar monotonicity, which means that longer expiries are worth more. We choose to work with the option price data because it's easier to impose these no arbitrage constraints on the price surface, as opposed to working with the implied volatility. We obtain the local volatility surface using the Dupire formula, where we need to take derivatives of this price surface with respect to both the maturity and the strike price. And then we sort of clamp this our data to sort of give us a good local volatility surface, which is defined on the same grid. which is basically the maturity and the strike price, and then we bilinear interpolate it for continuous queries. We have a local volatility surface now, so we can use those local volatility data to also price our options. So substituting it back into the formula for the options price, essentially, which is a risk neutral PDE, we solve this PDE numerically backward in time with the boundary condition that at the maturity it should be essentially be equals to the payoff of the option, whether it's a call or a put. And we use the Crank-Nicolson scheme to solve this new PDE numerically. And our Greeks are also priced as has shown over here in the slide. So in particular, we obtain the delta and the gamma. So let's do some look at some pricing diagnostics. We can see that our PDE price follows the market mid price very closely. So that means as a first look, our PDE price seems to be performing well. Pricing model seems to be performing well. We can also see the error distribution histogram on the right hand side. Most of the errors are concentrated around 0, so that's already a good sign that our PDE pricing model is performing well. On the other hand, there are long tail spreads, which suggests that perhaps some more tweaking of the parameters is needed to sort of get a more concentrated histogram around the 0. We can also look at the error versus maturity and error versus moneyness. We see that the error is on average is lower for lower maturities, but it is higher. It's much larger for larger maturities. We also see that compared to has plotted with moneyness, the error more or less stays constant, but the error does seem to increase with moneyness for higher maturity options. So right now we have essentially 3 models. We have our arbitrage-free pricing surface that we fitted. We have the local volatility PDE. We have the PDE that we use to price our options using the local volatilities. And then finally, we have a BSM baseline. That is just the conventional Black-Scholes baseline. And we see that on average, these 2 models are already performing better than the Black-Scholes models. We can also look at the model performance by tenor bucket. Tenor is essentially the time to expiry. And the moneyness bucket, with moneyness is just basically tells us how close we are to the strike price, how close, yeah. So we can see that on average, the RMSE, which is the error, is less than the BSM for all the buckets, for all the bins in each of the buckets. We can also look at some diagnostics for the Greeks. We see that the delta versus moneyness essentially has 2 branches. What I think is happening is it's because of the 2 different kind of options, the call and the put options that we are looking at, that we are seeing these 2 kind of branches. When we look at the theta versus moneyness plots, we see that there's a substantial difference between our PDE model and the Black-Scholes model, but they are both negative, so that's already good. For the gamma versus moneyness case, also again they're both positive, and once more there happen to be 2 different branches, which I think might correspond to calls and puts. So let me be further clear on what my baseline model will be going ahead. It's going to be the Black-Scholes, but with a sticky volatility. And by sticky volatility, I just mean I'm using the implied volatility for the day 0. And then I have written over here the usual formula for the Black-Scholes. And our hedging strategy will be that we will match to the market. So we will do a market hedged PNL. We are comparing with the price of the change in the price of the option in the market, the actual market data. And once more, like I've written over here the formulas for the RMSE and the MAE, and we can they essentially tell us how good or how bad our PNL strategy is. So we can, I have made use of the HPC facilities at my university in order to run this backtesting. The reason being that for a single day, the backtesting takes around 12 hours. So for a 21-day period, it would roughly take around 5.5 hours. But because of the fact that I was able to parallelize my code, I essentially got the runtime down from 5 to 6 hours to almost 12 minutes. So that's already substantial. That allows me to also do backtesting quickly and sort of play around with the parameters. So that's something that I will be doing in the coming days. But for now, I have over here for you like to 21 day, essentially the data for over a month. And you can already see that my model, the PDE model, is sort of straddling around with the BSM RMSE. So it's quite close. And actually, you can see from the rolling 1-day hedged PNL that actually at some point it performs on par or even better than the BSM, but after some time it kind of goes down due to the large spikes in RMSE and in the later part of the month. So uh, for future work, I would like to continue with this and look at some local stochastic volatility models. The reason I did not do that over here is because they are more well suited for FX options. Since I was just looking at vanilla options for this project, and that's the data that I had access to, I chose to stick with local volatility. But as a future work, that is something that I would like to look into. So thank you so much, and